Let's start off by first reviewing the right-hand rule. You don't have to copy this down because you've seen it before. But let's say we have a bar magnet, and we have a second bar magnet, and we'll make it into a three-dimensional drawing. Whoopsie. And let's say these bar magnets are anchored down, they can't move. So that's the south, that's the north. This is the south, this is the north. And now we're going to have like a wire going like in between the two. And let's say the conventional current is coming out of the page. If you want to visualize the invisible magnetic field lines going across, now take a moment to use your third right hand rule, keeping your hand flat, fingers and thumb at a right angle to each other. You put your fingers in the direction of the invisible magnetic force field lines due to the external bar magnets. Twist your hand until your thumb is in the direction of the current, and then the force magically comes out of the palm of your hand. Okay? In this case, what would be the direction of that current? Paul? Pardon? Up. It would be up. My fingers move to south, my thumb is kind of coming out of the page. Force would be up. So the force would be up. Now, if you think about it, people, what's flowing through the wires is that conventional current. And I know we talked about how there really isn't a positive charge flow, but mathematically the positive charge flow is equivalent to the negative charge flow in the other direction. But we've been thinking about current as, a fictitious positive charge flow. Where the charges are moving down the wire like that. So I drew some positive charges going down through the wire like that. And here's the thing. Those charges don't have to be in a wire to experience a magnetic force. So what if we had those same positive charges going between those two bar magnets, but not in the wire? Exactly. So let's just take some stuff away here. Actually, you know what? We'll leave that here, and we can insert a duplicate page, and then I guess that's all we go. So basically this time we're going to have positively charged particles we're going to have positively charged particles flowing the same way, but now they're not flowing inside of a wire. They're just like freely moving through the two bar magnets. And we can apply that same right-hand rule to figure out the force on those charged particles. But this time, instead of putting your thumb in the direction of the current, you're going to put your thumb in the direction that the positive charges are moving. So you would put your fingers in the direction of the bar magnet's magnetic field lines. and you would put your thumb in the direction that the charges are moving out of the page. And once again, what would be the direction of the force? My man Dylan. Up. Just like before, the force would be up. So we don't need no stinking wire to have a magnetic force on moving charged particles. If we wanted to calculate that force, there's a formula, just like there was a formula when there was the wire. Let's first go back and recall the formula for the wire. Oh, I thought I duplicated the page. I guess I didn't. Alright, we don't have that page. What was that for the, when you had the wire between the bar magnets and it experienced the force? What was the formula? That's right. Nice job, Brett. I/L/B sine theta. Where I is the current in the wire, L was the length of the wire that's in the magnetic field, B is the strength of the bar magnets, and theta was the angle between the current direction and the magnetic field line directions. Now back to today's lesson. The force on each particle is equal to Q, lowercase v, capital B, sine theta. Q is the charge on each particle. V is the velocity of each particle. B, just like yesterday, is the strength of the external magnetic field, the magnetic field due to the bar magnets. But this time, theta is the angle between the velocity of the charged particles and the bar magnets magnetic field lines. Yes. Yesterday the angle was between the current direction and the bar magnets magnetic field lines. Today, the direction is between the charged particle's velocity and the bar magnet's magnetic field lines. Now, what if the charged particles weren't positive? What if we shot negatively charged particles through there? It becomes a left-hand rule. And to find the force direction, you would use your left hand. So anytime you're trying to figure out the direction and the charged particles are positive, you use your right hand. And anytime you're using negatively charged particles, it would become a left-hand problem. So let's make a note of that. and then apply it to a problem. Right hand for positive particles. Left hand for negative particles. And this, of course, is to get the direction of magnetic force. So let's say we have this magnetic field going into the page. And let's say we shoot an electron into the magnetic field, so that when the electron gets here, it's moving with a velocity to the right. Since it's a negatively charged particle, if you wanted to find the direction of the magnetic force on that moving electron, you would use your left hand. And once again, take your left hand, keep your fingers and your thumb at a right angle to each other. Put your fingers in the direction, whoa, put that chair there, of the bar magnetic field lines, in this case, into the page. Your thumb goes in the direction of the velocity of the negatively charged particles, and the force magically comes out of the palm of your hand. Yes? So the force would be this way. Since there would be a downward force on that negatively charged particle, would it keep on going straight? Will it keep on going straight right on through that magnetic field? No, it's going to start to deflect downward. It's going to be curved downward because of that downward force. So the next thing you know, that charged particle, it's going to start curving downward. And when it gets here, it's going to have a velocity this way. Check out the direction of the magnetic force on the negatively charged particle in the magnetic field going into the page now. Wow, that was a long sentence. Which way would the magnetic force be now? Let's go to the back. Mike. To the left. Wait a minute. What's going on here? It's going down now, but there's a force going to the left. That's going to make it kind of like start moving to the left. Yes? You know, and let's say the magnetic field was over here as well. Now when it gets down here, going this way, which way is the force going to be now, Claire? Upwards. Oh, that's what I like to hear, ladies and gentlemen. The magnetic force becomes what kind of force, Paul? A centripetal force. It causes the particle to go in a circular path. Who knew that we would be doing circular motion in the magnetic unit? You gotta love physics. It's all connected. So if you wanted to calculate that force, of course, that force is equal to, and let me make some space up here, or actually I'll just go to the next page. That force is equal to qvB sine theta. And in this case, what would theta be? Theta is the angle between the magnetic field lines, which are going into the page, and the velocity, which is like going this way. 90 degrees. Notice it's always 90 degrees. Yes? So basically, in this case, the velocity is always at a right angle to the magnetic field. So basically our sine theta is going to drop out, because it's going to be the sine of 90 degrees. And the sine of 90 degrees is 0. Oops, no. Sine of 90 degrees is 1. Sometimes this is called the force due to the magnetic field, so F sub B, the force due to the magnetic field. So the force due to the magnetic field is qvB, but we know that's going to be providing the centripetal force. Now let's see who can recall the good old centripetal force formula, a little blast from the past. Yeah? I see that hand start to go up. Fc equals close over R. mv squared. You had it going right there. Awesome memory. Over R, the radius of the curvature. So let me bottom line it for you, people. The qvB turns out to be equal to the mv squared over R. And it turns out that this setup right here, folks, where you shoot the electron in the magnetic field, if you know the velocity of the electron and the strength of the magnetic field and the charge of the electron, and how would they have known the charge of the electron? From the Millikan oil drop experiment. If you knew all those things, you could use that formula on the next page to determine the mass of the electron. So basically, this technique of shooting a charged particle into a magnetic field and measuring the radius of the circle it makes, you could use this technique to get the mass. And that's how the mass of the electron was first determined. So this technique is used, to get the mass. In other words, you'll be given all the other variable information and be asked to solve for the mass. So let's end on one final question. Let's say this time we have a magnetic field that's coming out of the page. Sometimes the magnetic field coming out of the page is shown as a dot, or sometimes it's shown as circles. I'm going to show it today as dots. So we have a magnetic field coming out of the page. And let's say we have a particle, that goes into this here, and when it goes into this, it ends up curving upward. So we have a B field out of the page. The question is it positive or negative? Don't shout it out. Give everyone time to think about this. This is the typical AP multiple choice question. Well, they'll show you that charged particle going into the field, and then they'll ask you, is it a positive charge or a negative charge? And what you have to do is see whether it fits the left-hand rule or the right-hand rule. What do you think, Sita? Alright, if it was negative, Okay, and my fingers have to go out of the board. See how my fingers are going out? It's positive, yeah. Because my fingers have to go out, my thumb is going to go the direction that the charged particle is going, and the force is going to be upward. So it turns out to be a positive charge. So this right here shows the direction of the centripetal force. And this only works out with your right hand because the fingers are going out, so therefore it's a positive charge. Okay, we'll pause there.